Welcome, everybody. Welcome to the Open USD Insiders live stream / Isaac Lab office hours. I look at my great co-host here, Eric. How you doing, Eric?
Yeah, doing
This
great.
is this is an exciting one. Just for people just tuning in right now, I'm going to cover some news really quick. But for this office hours, we have some very special guests from NVIDIA. We're going to take a closer look at NVIDIA Isaac Groot Mimic. So if people aren't familiar with that, we'll post a blog in the live stream. We recently had a nice announcement about it, but it's for robot motion and trajectory generation. We're gonna cover all the basics with our guests in just a few minutes. But first, let's get started talking about a nice event that's coming up in Europe, GTC Paris, June 10th to 12th. We are super excited about this. Registrations are rolling in. We have some great content planned for GTC Paris. For everyone who couldn't make it over to GTC in San Jose in March, this event is for you. We already have several ambassadors from the Omniverse community that are going to be attending, including Michael Wagner, I think Scott Dempsey, I believe Pekka Varis, Alici AI, otherwise known as real name Muammar Bey, who I believe I just saw in the chat. All these folks will be coming. We're even talking about maybe doing an Omniverse meetup. So let us know if you're planning to come to GTC Paris. There's a QR code right now if you want to see. Oh, let me turn the chat off for a second so you guys can see the QR code. There you go. There's a QR code so you can grab it. We're going to test out this new feature today of showing the live chat scrolling on the screen. We'll see how it goes. So everyone out there behave, including you, Papa Chuck. I'm looking at you. All right.
I would say especially you, Papa.
Yes, especially Papa Chuck. So one of the cool things that happening at GTC Paris is actually there's going to be some amazing trainings and certifications. The ticket for GTC Paris is actually cheap, itself, but also these trainings are also discounted. So very affordable trainings and certifications available at GTC Paris. If you hit that QR code, you'll be able to find more details about each of the areas there. There's a bunch of them. They look really good. If we have time towards the end of the live stream, maybe I'll bring up the website and we can look at them together. But I highly recommend that everyone who can swing GTC Paris. It's going to be an amazing event, especially for people who didn't get to come to GTC in March. These are some great community resources converted into QR codes by our great friend Mara from the social marketing team. So these QR codes will bring you to several different destinations. Our event calendar, where all of our upcoming live streams and office hours are, our forums, where you get official support, our Discord server, where the community hangs out, an amazing place to come and meet and share your projects, and our community page, where you can see the listings of all of our ambassadors, who I just mentioned a few minutes ago. Really, really helpful resources. Let me know if you want any of these in the chat. We will share them again in a second. But Eric, we have an exciting show planned today. I'm so glad you're here because you're the perfect person to engage with these experts we have. Isaac, obviously, there's so much excitement over Isaac Sim and Isaac Lab. Why don't we do this really quick for the people who are just tuning in? How would you define Isaac Sim and how do you define Isaac Lab? And then I'll bring in our special guests.
Well, Isaac Sim is a robotics simulator. So it's like a virtual world where you can simulate robots. And Isaac Lab is a robot trainer. So you can use Isaac Lab to orchestrate training runs and train robots. So in Isaac Lab, we'll use Isaac Sim for its simulations.
Okay, perfect. So that's a great way to define it. And so today we are going to be pretty squarely focused on Isaac Lab. So we have other office hours dedicated to Isaac Sim, and we have an Isaac Sim channel in Discord. So feel free to check out those resources. But why don't we go ahead and get the party started with our other NVIDIA guests of honor here. Oyinda and Peter, thank you so much for coming today. Oyinda is no stranger to these live streams. She actually has a nice fan club that's already in full swing. But why don't you introduce yourself for people who maybe didn't catch your most recent appearances on the live stream, and tell a bit about your background, what you do at NVIDIA, and also what you're going to be focusing on today. And then we'll let Peter also do the same.
Okay, thank you, Edma. All right, it's good to be back here. My name is Oyinda Mola, and I'm a robotics technical marketing engineer at NVIDIA here. So I focus on Isaac Sim and Isaac Lab, and majorly right now on Groot workflows, which we are going to be focusing right on to this live stream. Thank you.
Amazing. Okay, so excited, and she's got some great slides in a couple minutes that will give us a nice overview to set the stage. Peter, this is your first appearance on the live stream, so welcome. We are very excited to have you here. Why don't you let everybody know about what your background is and your role in the team and what you'll be covering?
Yeah, thanks, Edmar. My name's Peter. I'm a robotics engineer at NVIDIA. My background's mostly in safe and robust autonomy, and I currently work on Groot Mimic. So that will be, we'll talk a lot more about that today, but essentially it's part of the larger NVIDIA synthetic manipulation motion generation blueprint. It's all about data generation for robot learning.
Awesome. That's fantastic. Okay, cool. So super exciting. So I already see a lot of great chats coming on. Let me turn this on really quick, see if it shows. So feel free to ask any questions you might have in the audience. Ask them live. If we don't get it right away, we'll try to hit towards the end of the live stream, but definitely keep the comments and questions coming throughout. Super helpful for us. Okay, so I think we have a nice little slideshow here. Here we go. Going over what is robot learning.
Okay. All right. I think I can just get started on that. Hi, everyone. Again, I believe that a lot of us, are familiar with robot learning in this place. Of course, it's a field of AI that enables robots to be able to learn tasks autonomously, using data and interaction with the environment. So today we just look at two different broad ways to be able to define robot learning algorithms. Of course, there are different ways to classify them, but we classify them into two broad ways, and then we focus on one of it, and that is where Groot Mimic is spawned from. And also, of course, why robot learning? It helps to reduce the need for manual programming, and robots can really adapt to changing environment. So the two broad ways is number one, imitation learning. So from the one imitation learning, you learn by mimicking demonstration, especially, for example, from humans. So for instance, if you're trying to teach a robot on how to perform assembly tasks in a factory, you need to show it a series of demonstration, either performed by a human using teleoperation or through videos or through different means in which the robot can actually learn different kind of demonstration. So this is one way of training your robot to be able to do a specific task. Of course, the other way, which we all are familiar with, is reinforcement learning. And this involves learning through trial and error by maximizing reward. So basically, you let the robot try out different things in the environment, and based on the task that you want to do, you give it a positive reward when the task is done and a negative reward when the task is not done. So for example, if you're teaching a robot how to grab an item, or maybe move locomotion, like move from one place to another. So like locomotion, distance can be a reward. The closer you are to distance, then you have a positive reward. The less close you are to the distance, you have a negative reward. And of course, it's good for like complex tasks, like if you're trying to combine grasping, locomotion, and manipulation all together. But the different other kind of algorithms, you can have like supervised learning, you can have unsupervised learning. But for the focus of this particular live stream, we'll look at imitation learning. So why imitation learning? Number one, recording a demonstration may be simpler than maybe defining a reward function. Because for instance, if you're using reinforcement learning, you need to first define a reward function. What is a good reward function can become a research engineering problem. So if you have an opportunity to record a demonstration, then maybe it's simpler than maybe defining a reward function in some cases. Now, what are the challenges? If you want to create a perfect demonstration, it can be really challenging. I don't know if any one of us have tried to tally up a robot in simulation to do a particular thing. It can really be challenging in terms of the time you have to.
I've never done that before. Have you done that before?
Oh, I've done that a couple of times.
Is it really hard?
I mean, it depends on the kind of setup you have. It's not hard, but it's time consuming. Like you need like maybe different human operators for maybe like depending on the number of demonstration you want to collect. And we know that you need a lot of data to be able to train a robot for it to actually perform the task. If you need like 10,000 of data sets, then you need like you can't get 10,000 of human beings working at the same time. So if you have just one human operator, imagine Edman trying to record, a humanoid robot trying to pick a task, 10,000 times. He's probably going to ask for lunch, dinner for at least the next 30 days. So it's kind of time consuming.
Seems like it might even be a little small.
Exactly.
Because I'm going to guess, because I think, I've never done imitation learning, but I've done a little, I have trained some classification models, just some image classification models. And even those simple image classification models might take in the thousands of images. And that to me seems simpler than an imitation learning policy. Is that right?
I mean, classification is a whole different ballgame than imitation learning.
Sure.
Because imitation learning, right here, you are dealing with robot and their actions, right? The robot needs to do something in the environment, and also getting those demonstrations is quite challenging, and sometimes robots may struggle with some situation they've not seen. So collecting this extensive high data set in the real world is tedious, time-consuming, and prohibitively sometimes expensive. So what do we do to solve them? One thing we are proposing today is generating synthetic data from physical accurate simulation that can help to accelerate the process. And this is why we introduce Isaac GR00T. So Isaac GR00T is NVIDIA development platform, also called Generalist Robot 00 Technology. It's a development platform for general purpose robot foundation models and data pipelines for humanoid robotics. Of course, some of the data pipelines can be applied to different embodiments, like say manipulators, single manipulators, bi-manipulators. So GR00T has different kind of components. We have foundation models, like a lot of us have heard of GR00T N1, and of course last Computex we also announced GR00T Dreams, and also we have synthetic motion and data generation pipeline, which we'll be focusing on today. The real question is, how do we generate data, or how do we scale up synthetic data in such a way that we can reduce the time it takes to be able to tally up those kind of situation, and in such a way that you can generate thousands of data sets in few hours. That kind of scaling up. And of course, under Isaac GR00T, we also have the platform Isaac Lab and Isaac Sim, which we've spoke about, and also Tor, Jetson Tor, which is our robotics computer for humanoid robotics. So I'll pass it over. Yeah, go ahead.
So is Isaac GR00T inside of Isaac? Is that like a Isaac Lab component, or is it completely its own thing?
Yeah, so Isaac GR00T is a whole project that has different workflows. So we have GR00T perception. There is actually a technical blog that we have which introduces Isaac GR00T, and also like the Isaac GR00T product page. I think I sent that to Edma. You can put the link on the channel. So it has different form of workflows. But for the synthetic data generation, like GR00T Mimic, it's embedded and implemented in Isaac Lab, and that is what we're going to be talking about today.
Okay.
Yeah, Peter, over to you.
Yeah,
If there are questions, please, you can put it on the chat, and we'll be happy to answer them.
Here's a good question right now before Peter gets started from Lychee AI, who I mentioned earlier, who's a great channel. How many trajectories episodes do we need to fine-tune a task like picking up a cube with a single manipulator?
Yeah, I can answer that. So we've done some tests with Groot Mimic to actually do that task. It's a cube stacking task. So for a task like this, we typically generate about 1,000 trajectories to train a model from scratch to do that task. For fine-tuning a task on an existing model, we also use on the order of a few hundred to maybe 1,000 trajectories. Now, as your task gets more complicated, as your scene diversity increases and you want your model to be more robust, that number can quickly grow. But you're looking at on the order of hundreds to thousands of trajectories for tasks like these.
Very helpful.
Now, Groot Mimic is like, I guess we're going to talk about that, but that is different from the GR00T Foundation model. Is that right?
Yes, that is different. So you can think of Groot Mimic as the thing that you use to feed the GR00T Foundation model with data. So
if you're going to take the GR00T Foundation model and refine it to your specific task.
Yes, exactly.
Got it.
Okay, I've got your slides up on the screen now, Peter.
All right, thanks, Edmar. So, hi everyone. Like I said, like I introduced before, my name is Peter. So I'll be talking about more in depth on NVIDIA Isaac GR00T Mimic, and specifically what it is, how it works, and kind of go through some demonstrations of how GR00T Mimic can be used to vastly scale and make your data pipeline and data campaigns more efficient for imitation learning. So kind of quick outline of the topics we'll be going into today. We'll do an introduction of GR00T Mimic, what it is, and how it works. and then we'll talk a little bit about the workflow and how the main steps to go from a couple of human demonstrations to a large corpus of generated training data for your robot model. We'll then try to do a live demo just of running annotation and doing data generation, and then discuss a little bit about some tips and tricks for how to maximize your data generation quality and success. And then at the end, we'll talk a little bit more about even more data expansion when we combine Groot Mimic with NVIDIA Cosmos World Foundation model. So with that, we'll get started and sort of first answer what exactly is Groot Mimic. So it is a synthetic motion generation pipeline, and it's a set of workflows to generate motion data from a small number of human teleoperated demonstrations. So as Oyedemola had mentioned, it's it's very tedious and time-consuming and expensive to have humans manually collect training data for your robot. So asking a person to collect 5 or 10 demonstrations, that's simple and easy. Asking them to collect 10,000 is much more difficult. So Groot Mimic will take, the point of Groot Mimic is to take a small number of human demonstrations that can be easily collected and collected of high quality, and then extrapolate from that to generate a much larger, a vast number of synthetic motion trajectories. And so this minimizes the challenges of developing very large data sets from human operators and reduces the data collection time by orders of magnitude. For Groot Mimic, we currently support manipulators and humanoid robots. So any kind of manipulation or humanoid task, we can automatically synthesize new trajectories.
So does it actually create? This is one thing, and you'll probably go over this. So if you're going to go over this in a few minutes, we can just wait till then. But it's creating new trajectories.
Yes, it's creating brand new trajectories. So you can think of it as if let's take this cube stacking task, for example, here. Let's say the human collects a demonstration where the cubes are in this in one particular configuration. The Groot Mimic algorithm will create a new trajectory for cubes in a completely different position using those existing human demos. So it's a new trajectory, but it's kind of created using the existing human ones.
This sounds like magic to me, I gotta say.
We'll go through how it works and how it transforms.
Sounds great, but I mean, wow. I'm really curious to see how this works. Yeah, I can't wait.
So before I kind of dive a bit deeper into how that all works, I'll kind of just briefly discuss here how Groot Mimic fits into the larger synthetic manipulation motion generation blueprint at NVIDIA. So Groot Mimic here is primarily a trajectory generator. So if you look at this entire pipeline of going from no data existing to a large data set, you start with first having a human do some teleoperation and collecting a set of good trajectories. And that is what we call Groot teleop. Once you have those human demonstrations, you can then use Groot Mimic to create a new set of motion trajectories. And this is done through Isaac Lab with accelerated physics engines and so on. Once you have those trajectories, you've already expanded your data set by an order of magnitude. But for more complex tasks and for more robust policies, you may want to go beyond that. And that's when we start talking about Groot Gen, which is using NVIDIA Cosmos to take the Groot Mimic trajectories and add a whole host of visual diversity to it. So things like changing the background, changing the colors of objects, and just basically expanding another order of magnitude on the dataset diversity. Today we'll focus mostly on Groot Mimic, and we'll talk a little bit about Cosmos and Groot Gen at the end. But that's kind of this leveled approach here, where we start with a single digit number or double digit number of human demos, go to thousands with Groot Mimic, and then go to hundreds of thousands or millions with Cosmos and Groot Gen.
And I'm guessing that as part of that, you specify which elements of the scene are randomized. Is that right?
Yes. Yes. So you can specify fully how your scene is created, what parts are randomized, and this is because Groot Mimic lives in Isaac Lab. So all the existing infrastructure for building up environments in Isaac Lab, that all translates to Groot Mimic. So you have full control over that.
So that's done through the in Isaac Lab. Whenever you reset a scene, you can randomize the scene, and that's done through that reset, kind of that same reset functionality, not through like the Isaac replicator functionality in Isaac Sim.
Correct. It's done through the reset functionality in Isaac Lab, not the replicate.
Cool.
So then let's talk a little bit about how Groot Mimic actually works. So the key idea here is that we take an existing task that is, in this case, human collected, and we divide that task into, or we slice it up into subtasks. So each subtask here you can think of as a portion of the trajectory where the robot is acting with respect to one particular object. So in this case, for the stacking task, we have 4 subtasks. The first task is trying to grasp the red cube. The second task is trying to stack the red cube, and so on. So each of these subtasks, the robot's motion is always with respect to a consistent object. And this is really what allows us to do this automated data generation. When we have a new scenario, so in this diagram here, you can see when we start out with a new scenario here, we look into our existing corpus of human demos, and we find one that is the closest to this current observation. And we'll talk a little bit more about what close means here, and there's different ways to define it. But for now, you can think of, we find the closest neighbor to this current observation. Once we have that, we know how the human demonstration looked in that scene. That's what you see here. We can then do a transformation on the trajectory from that human demonstration to make it match our current scene. And that's what this diagram here shows. We take this trajectory here for the blue mug, and we transform it to match our current scene. Once we do that transformation, the robot's current position may not be at where that new trajectory starts. And so to bridge that gap, we then do interpolation to basically move the robot to the start of that new trajectory. And then from there, we can execute that trajectory and hopefully, recreate or recreate successfully that particular subtask. And we do this for every single subtask in the scene. And once we stitch them together, we get a new trajectory. We run that trajectory through Isaac Lab, and at the end of it, we can say whether or not that trajectory was successful. If it was successful, we'll go ahead and save the trajectory as part of our new data set. And if not, we'll discard it and try again. So then the workflow then for Mimic is basically divided up into 3 steps. We start with data recording, which is where a human teleoperator goes ahead and records high-quality demonstrations of that task in Isaac Lab. And like I said, we support manipulators as well as humanoid robots. And so we have a variety of supported devices that users can use to collect that data set, keyboard, space mice, or a VR headset. And so this is basically, you want to use a device that gives you the best quality demonstration for your particular task. Groot Mimic doesn't work well if you don't give it good trajectories to begin with. And this step, typically for an experienced user, takes on the order of 10, 20, 30 minutes. You don't need to collect a lot of demonstrations. We typically collect somewhere between 5 to 20 demonstrations to generate 1,000 demos, for example.
Wow, that's not very many.
Yeah, the point here really is to minimize the burden of human data collection.
And I'm guessing you could use a leader follower arm configuration too.
Sorry, what do you mean by that?
Oh, like sometimes, like with the SO101 arm, sometimes you can get a leader and a follower arm, and then you can use the leader arm to teleoperate a follower arm and use.
Oh, yeah, exactly. So you can basically teleoperation. We provide a set of devices, but whatever, if you have a different environment and you have a different style teleop that works for you, that can be very easily integrated into Isaac Lab. And basically, as long as you can get good demonstrations, the exact method there is intuitive.
And you use Isaac Lab to record those? I haven't recorded demonstrations for imitation learning. Is that Isaac Lab?
We use Isaac Lab. Yeah, we have a set of scripts existing in Isaac Lab that kind of guides users how to do this.
Cool.
After you record the data, the next step is to annotate that data. Like I described before, the key thing that makes this all work is that we can divide data sets into subtasks. And so this division we call data annotation. And so once you've collected your human data set, you go through and you annotate that data set to indicate where each subtask ends. And that splits up the data set ready for Groot Mimic data generation. Now, this can be done automatically or manually by humans. I'd say typically for simple tasks, it's easy to write a condition to do this automatically, but for more complex tasks, such as the one shown here, where you have a humanoid picking up various objects, it's actually easier to do manual annotation. And we'll go through a demo later today where we actually do manual annotation over this, and you can see kind of how that all works. And this step here, because you have a small number of human demonstrations, is usually very quick, on the order of minutes. And then lastly, once you've recorded the data and entered the data, that's kind of the extent of manual intervention. The rest is all automated. So you can automatically generate new demonstrations by sampling from some initial condition that the user provides. And for data generation, because we're running an Isaac Lab, we're able to do this in parallel. So when you run data generation, you can run tens or hundreds, depending on the complexity of your environment, of environments in parallel, and that speeds up data generation significantly. So think of the amount of time it takes to generate one demo. If you're doing it over 100 environments, that cuts it by a factor of that increases by a factor of 100. So to show kind of an example or a working example of this, we did this entire Groot Mimic pipeline for a Franca ARM to do a cube stacking task, where we had a human teleoperator collect 10 demonstrations of them stacking the task. We then scaled up this data set using Groot Mimic and generated 1,000 new trajectories. And then we use these trajectories to train the BCRNN visual motor policy to perform that stacking task. So existing already available in Isaac Lab, we have this workflow where you can run this entire workflow starting from human demonstrations to end-train policy to really see how this pipeline can benefit and simplify your data strategies. All right, so with that said, I guess first off, is there any questions?
Wow, we got a bunch.
Loads of them, yeah.
Let me see. Let's start. Okay, so one, let me see. I think, okay, great. Amelia's been starring these. So thank you, Amelia. Let's a couple of them we answered in the chat. So let us know if you need us to reiterate anything there. Here's one that right off the bat, what would be a GPU requirement?
Yeah, so we recommend for running a decent amount of parallel environments, something like a 4090 minimum, preferably an RTX 6000. So the precise requirements is quite flexible. So because we can run a variable number of environments in parallel, if you have the GPU with less VRAM, then you just run a smaller number of environments. But for our use case, when we run locally, typically 4090 is the minimum to get a good number of parallel environments.
And I think you said that with that 4090, it would take a few hours to generate those parallel environments.
Yeah. So with that 4090, to do this cube stacking task, depending on whether you do a fully state-based or a visual motor policy, that data generation will range from maybe 30 to 45 minutes to a couple hours. So if you have more complex environments that requires more rendering, it slows it down a little bit.
And so with the state-based, so you're saying that you can train it, because I know in reinforcement learning, you kind of there we work with observations, right?
Yeah.
And it's kind of a similar concept in that the question might be, as inputs to your neural network, you're going to have some data, and that could be like a privileged state information, like it knows where the cubes are, it knows where the positions of the motors, or it could be just like image data from some sensors. Is that right?
Yeah. Yeah.
And
So
it's going to take, it's quite a bit harder to train than having that privileged state information. Is that right?
Exactly. Yeah. So if you do a fully state-based policy, where in simulation we can obviously collect that data for the data set, positions of all the objects with ground truth, that will be easier to train. And however, if you wanted to deploy that in real, without having that ground truth information, you would need state estimators, object detection, things like that. On the flip side, if you don't have that and want to train a purely vision-based policy, which is the example we show here, where the robot is just using two cameras, one mounted on the robot, one mounted overhead, then that takes a little bit longer to train, takes a little bit longer to generate the data set, but then you don't need those additional things when you're actually doing the deployment of the policy.
Got it. And I bet there's a lively debate on whether it's better to use a state estimator or to just train a vision policy directly.
Yeah, definitely. We won't go too much into that right now, but, but it's very much dependent on the capabilities of your state estimators and your detectors.
Sure.
Okay, we have another great question here. What determines a high quality data set?
Yeah, so I assume you're referring to the human, when I say kind of high quality human demos. So this is a bit of a, I guess this term here, there's not exactly a strict benchmark or criteria here. When I say high quality, what I really mean is, so if you want your robot policy to perform a certain way, and you want, let's say, the robot to do a task in a specific way, your human data should match that. Your human data should kind of give it the best shot to learn that behavior. And so when I say high quality here, I really mean that the data should be catered to your needs. And when you look at that data set, you should think, okay, if my robot did this and it recreated this kind of behavior, I'd be satisfied. So that's what I mean by high quality. Now, from a data generation perspective, if you want high data generation success rates, there's also kind of a quality aspect there. If your human demonstrations are very jerky and very kind of not very smooth, maybe that is high quality to you because you want your robot to learn that. But from a data generation perspective, that's going to make it more difficult, and you're going to have more failure rates when you generate the data set.
Okay, super helpful. All right, great questions in the audience, so keep them coming. We answered this in the chat, but for anyone who might be wondering the same thing but didn't post regarding Apple Vision Pro support or Quest 3. So Apple Vision Pro is a supported device right now. However, there are future devices planned in upcoming releases. So just stay tuned, unless Peter or Eric, you have to add to that.
Well, I was just going to, that's the supported VR device. I think you could use like a 3D mouse or
Space Mouse,
a leader arm, or
Yeah.
like a gamepad. There's any number of ways to generate those, but it sounds like as far as like a VR headset.
VR, yes, correct. That's great to see that Space Mouse is supported, though. I know we have a lot of fans of Space Mouse in the community.
Yeah.
We started with Space Mouse for the Franca arm, and then once we introduced humanoids, we had to add in the Apple Vision Pro because it's kind of hard to control two space mice for two arms.
Yeah, that would be confusing.
All right, you got a comment from LinkedIn from Krishna. Would a manipulator include an industrial robot?
Yes. So here, when we say manipulator here, basically any robot that you can add to the Isaac lab environment. It doesn't have to be, in this example we show a Franca arm, it doesn't have to be this one. It could be a UR robot, for example. So because this is built in Isaac lab, you can bring in basically any robot that you want, and as long as you add that to the environment, they would have support.
And I'm guessing it should probably be like a robot arm that can support some sort of an open standard like ROS, rather than like some of the industrial robotic arms are more like PLC based and more rigid? Is that
Yeah, so the controller here is something that, so it doesn't have to be in ROS, for example. The main requirements for Mimic is that the robot has a controller that where we can give it an end effector pose in task space, and the robot has a controller that can then do that. So as long as that controller is implemented somehow, the Mimic algorithm can support it.
so you can have receive state, run that state through your policy, and get back and you get back some commands, and then as long as you can write those commands to the ARM, you're good to go.
Yeah, and the key thing here is that those commands at some point those commands need to be translated into task space or end effector space poses. So that transformation that I talked about with how Mimic takes an existing human demonstration, does a transformation, does interpolation, that is dependent on those poses being in XYZ and in orientation. If you just give it a pure robot joint state, for example, it wouldn't be able to do that because we wouldn't be able to do the transformations.
Right. Yeah, it's got to be in Cartesian space so that you can like flip that trajectory in the opposite direction, and those sort of. It reminds me of the data augmentation with images, right? Where in a way you can flip images, you can crop images, you can do all these things. You've almost like reimagined those transformations in this like more complex 3D space.
Yeah, it's kind of a similar kind of a spirit to that, but kind of done for motion instead of images.
But like a bajillion times harder to figure out. That's so cool. I have no idea how you guys figured this out. That is amazing. I'm just like, my mind is blown today.
I could tell with a lot of interest and people want to dive in the chat, which is great. So keep the questions and the comments coming. Here's one from YouTube. I need to calculate my own FK and IK kinematics to build a personal robotic arm and train on Isaac Groot. I guess she's asking. Sorry, I read that wrong. I should have asked it like a question. How do you want to answer this one?
Yes. So for IK, we have controllers built into Isaac Lab for that. So you don't need to calculate your own. We have an existing Python IK-based controller for that. If you were to bring a new robot and you wanted to sub that in with a different forward and inverse kinematic solver, and that you think is more performant or maybe suits your needs better, that's also completely flexible. But you don't have to develop your own kinematics solvers for if you wanted to use Groot Mimic as is right now.
Great. Okay. Thank you for answering that. Here we got another question from LinkedIn. Love how Groot Mimic bridges physical motion capture with high fidelity digital replication. Curious to see how that evolves on lower power platforms. I guess it's just more of a comment. But yeah, I guess we can always expect optimizations to come. Naturally.
Yeah. So yeah, in the future, we will be making optimizations to things like rendering and telecameras, all those things to kind of bring down some of the computational costs. Ultimately, though, I think for this kind of scale of data generation, it's very difficult to make it extremely kind of low compute, since this is this is kind of the step where you're generating thousands or millions of data points, and so it's one that is not viewed as something that you would run on, let's say, an embedded platform. You probably want to run this on some sort of larger compute cluster. And then once you actually train your model and you have a model that you want to distill down to maybe run on lower power platforms, that's kind of a separate step there. So we do have optimizations, but I think ultimately, if you want to generate a lot of data and you want to do it massively in parallel, it's going to require a good amount of compute.
Very cool. I apologize, Oyinda, about every time a comment comes on, your face disappears. I wish we could switch. I'd gladly give my face away. Okay, another question from YouTube here. Do you need to do the subtask split manually, or does Groot Mimic do that itself?
Yeah. So the subtask splits can be done both manually and automatically. When it's done automatically, what I mean by that is that the subtask conditions are built into the environment. So if the environment has that capability built in, then you can run basically data sets through it, and it will automatically annotate your demonstrations according to those subtasks that were defined. So ultimately, it's still you who gets to decide how to split those subtasks. However, if you don't want to create these conditions to split subtasks and you want to have more flexibility, you can also replay those human demonstrations manually and then mark manually, which I'll show in a bit, and you can mark those subtasks manually. So I would say for more complex tasks that involve maybe a humanoid, it's actually easier to mark it manually. Mimic has a decent amount of robustness to the precise point where you mark subtasks. If it's a little bit off by a couple time steps, the algorithm is completely robust to that. So you have some flexibility there.
Great. Okay, cool. And it was nicely reminded about the time here. So we have about 20 minutes left. I'll make sure we're covering everything you want to cover, Peter, in the live stream. So maybe we can pause on the questions and then circle back if we have time at the end.
Yeah, sounds good. So with that, then I'll move on to the kind of example here. So in this example, we'll go through the Groot Mimic pipeline for this particular task, which is using a Fourier GR1 humanoid robot to do this pick, pour, and then place task. So we'll kind of start by going through annotation, how that works. I know this is a question that comes up a lot with Groot Mimic, which is how do we actually go and annotate these trajectories, and how do you do it in such a way that is good for data generation? So for this particular example, we have a humanoid, so we have two end effectors. We have the left arm and we have the right arm. Each arm has its own set of subtasks. So in the right arm, for this case, we have essentially three subtasks. We have this initial idle position where the right arm is waiting for the left arm to complete. And then it goes and it grasps the yellow bowl, and then it places the bowl onto the pad. For the left arm, it has two subtasks. It basically grasps this red beaker, and then it does a pouring motion, and it places the beaker into the blue bin. So in Mimic, when we talk about annotation, what we're really saying here is that the annotation should represent the end of a subtask. So when I say annotate let's say I ask you to annotate the idle subtask for the right arm. What I'm referring to here is mark the position in the data set where the idle subtask for the right arm has completed. And this is how the annotation script will work as well. Each time you mark an annotation, that denotes when a subtask has ended. So with that, let me actually switch my screen over here to do a demonstration of that. Let me bring this back here so that we can have reference it when we need. So we've gone ahead and collected a data set of 5 human demos for this particular task. And I'll go ahead here and run the annotation script. Also, just as a note, all of these commands and these tutorials, we have it available on the Isaac Lab documentation. So online, you'll be able to kind of have a tutorial to do similar things, and you don't have to copy down these commands from the video. So this is our environment that we have. We have the humanoid environment in the Isaac Sim window here. And you can see when we first start up annotation, the robot is in a pause state, and it loads in the first demonstration here, in this case, episode 0. And it'll indicate to you which subtasks you're trying to annotate for. In this case, we're currently annotating for the right end effector, the right arm. And it tells you the subtask terms here. It's idle right and grasp right. Note that in the previous slide, if I go back here, I actually said that there were 3 subtasks, but here we're only annotating 2. And that's because each annotation denotes the end of a subtask. So implicitly, the end of the place subtask, it's the end of the data set. So you don't need to annotate that explicitly. It's already kind of embedded there by this definition of what an annotation means. So if we go back to the Isaac Sim window, we can see here that to start the annotation process, I can press the N button on my keyboard, and that will start replaying the trajectory. At any point in time, if I wanted to pause this replay, I can press B, and that pauses the trajectory. When I'm ready to annotate a subtask, I can press the S key on my keyboard, and that will annotate and add in that marking for the subtask. So I'll let this play out right now. And right now we're trying to annotate for the end of the idle write subtask. So that subtask will end right after the left hand finishes its task and places the beaker. So right after this, I will do my first annotation. So right here, I'll annotate the first subtask. And the second subtask is grasping the bowl. So after the right hand grasps the bowl, I'll add in my second annotation. So that completes the annotation for the right arm. We do the exact same process now for the left arm. So we can see that the end effector now has switched over to the left arm. And now there's only a single annotation we need to do, which is grasp left. Again, the last subtask is implicitly defined in the data set. So I'll do the exact same thing. I'll play the data set, let it grasp the beaker, and then once it's grasped, I mark the annotation right there. And then this will run for the remainder of this trajectory.
And this is, yeah, that's even that manual annotation seems fairly easy.
Yeah, so the manual annotation is it's relatively straightforward, and like I said, it doesn't need to be extremely precise. Like in this case, you don't have to get it at a very, very precise time step. You just kind of need to get it once the motion has been completed. And the Mimic algorithm, because it's stitching together and doing these interpolations, has a level of robustness to when you mark those subtasks. So basically now we've finished annotating all the subtasks for the first demonstration. We would do this now for the remaining human demonstrations. I won't go through that kind of on the live demo for time purposes. But it's the exact same procedure. You do it for the remaining 4 demonstrations. Once you've annotated the demonstrations, you can then go ahead and run data generation. So I've kind of I prepared a set of pre-annotated data, and I'll run data generation here. So using that annotated data set, I can run data generation to create new trajectories. And here I'll run data generation with 4 environments in parallel. You can do more. 4 here just as a kind of a not too many to visualize. But you can see once the simulation loads up, it will automatically load in the annotated data set and start to do new data generation. So you can see here, each of the environments here starts up. And this motion now is coming from the transform and interpolated motion of the annotated demos. So one thing you might notice is that the robot's arms here are they're slightly shaky, slightly wobbling there, and that's done on purpose. So during data generation, we typically include action noise into the trajectories, and this allows typically to train policies that are more robust to slight deviations in the robot's behavior. So this action noise is fully customizable by the user. If you want more, if you want less, you can customize that fully to your own taste. Usually after you generate the data set and you train the policy itself will learn to smooth out this the policy will learn the mean of this distribution, and you won't usually see this noise in the trained policy. But you see here, we're generating data with these 4 environments and those annotated demonstrations, and we can let this run to generate however many demonstrations we want. So currently you can see this is running with full simulation, and it's running with full visualizations. If you're actually trying to generate a data set, what you would do is you would usually run this headless. So you would run this without this full Isaac Sim visualization and rendering, and that will allow you to run a larger number of environments in parallel, as well as run it much quicker. So you see here, we'll continue to generate the data set, and this will go on. Now, once the data set is generated, we have tools in Isaac Lab to visualize that data. So here we have a replay script that we can use to view the generated data. And this replay script works similar to the annotation script in that we can play and pause the demonstrations or the replay as it's running. And this just allows you to visualize the actual data sets that you generate. It doesn't necessarily have to be for generated data. You could also use this to visualize your collected human trajectories. But you can see here, this is the data that we generated with the action noise and the slight wobbling in the robot.
So can you choose how many environments you replay here, or is it always one?
Exactly. We can choose a number of environments. You can choose to replay with a larger number of environments. That's fully user specified.
Cool.
And then the last thing I'll quickly show here is an example of a policy that we trained using a generated data set. So if we had let that data generation run for the until completion, it would have created 1,000 demonstrations. And we trained a LSTM policy from scratch using those 1,000 demos. And this is the resulting policy of from that Groot Mimic generated data set. So again, all of these scripts are available in Isaac Lab. We provide a tutorial for how to do this from scratch on your own machine. So it'll go through all the steps from human data collection, annotation, generation, through to this policy training as well. As you see here, the train policy here, it's learned to smooth out that action noise, and it doesn't have that shaky behavior anymore.
And does it randomize the positions of the items on the table, or in this example?
Yes, it's randomizing the positions of the objects on the table. That is something that you can specify in the environment itself. So the environments are just standard Isaac Lab environments, and so in this case, the randomization here. If you look here, this is the environment that I was just running. In here we have a bunch of reset events, and one of them is to randomize the objects. So here we have a small amount of randomization, a couple centimeters. We can turn this up to larger values. And one of the nice things about Mimic is that we can add in larger reset distributions and run data generation without having to recollect the human demonstrations. So here I've increased the reset distribution here, and we can actually run generation again using that larger reset distribution, using the exact same human demonstrations that had the smaller reset distribution, and we're still able to generate data.
I'm guessing that if you made that randomization much larger than your demonstrations, would you at some point run into trouble and need demonstrations with a little greater variability as well?
Yeah, exactly. So it's robust to a certain limit, but at a certain point, if you start to have very, very large deviations between your generation environment and your human demo environment, then you might run into the case of a lot of failures, where in that case, you'll probably want to recollect your human demonstrations to be more to match that more. But in this case, adding in a few more centimeters of randomization, you can see that it's still able to perform the task and do it relatively successfully. All right, so with that, I will wrap up the demonstration part of things, and we'll move on to the next section. So we get quite a lot of questions asked about how do you tune the parameters of Mimic data generation to get kind of good quality data and high success rates. One of the main questions that we get a lot is, how do you split subtasks? So we've kind of said, you have to split your trajectories into subtasks, but you can actually do this in a number of different ways, right? We don't tell you for each task, this is the number of subtasks you need. It's variable and dependent on the task. And so that gives users a lot of freedom, but it also gives, you a lot of freedom to split subtasks in a way that is bad for data generation, bad for the quality of your end data set. The general rule of thumb that we try to convey is that for good synthetic data generation, you want to minimize the number of subtasks. And that's because if you have more subtasks, in theory, you can do transformations and interpolations and stitch them all together. But each time you have that transition, you have basically a discontinuity there that you have to bridge. And so the more subtasks you have, the more stitching of trajectories, the less smooth the trajectories, and the higher the failure rate. So at the minimum number of subtasks you need can kind of be answered by this question, which is for every motion in your trajectory, you want to ask, is the end effector or the arm dependent on a different object whose position may have changed? If this is ever true, like if this transition ever happens, then that's when you must start a new subtask. You cannot have that trajectory all be part of one subtask. If the answer to that question is false, you can keep the same subtask. And so sort of using that heuristic, you can then determine what is the minimum number of subtasks needed for my trajectory. The other thing regarding subtasks that I want to kind of come back to is, if we recall from earlier this diagram, once we select the human demonstration, in this case, this demonstration for the blue mug, and we transform it to the current scene, you can see that there is this interpolation segment because the robot may not be at the position of where it should be starting. This interpolation is something that has to be added in by Mimic. And so this interpolation is something that needs to also be tuned and tailored for good data generation. If we split subtasks in such a way where this interpolation is happening when there could be a collision between the robot and another object, then this tends to lead to unpredictable or undesirable trajectories. In this case, you can see that we have this robot trying to grasp the beaker, and we're on the left, we split the subtask right as the hand grabs the beaker. So the beaker is still on the table. On the left, we split the subtask after the robot has picked up the beaker and moved it upwards a little bit. You can see here, because of interpolation, on the left, the subtask results in the robot's hand hitting the table and kind of lagging a little bit as it's not able to move. Whereas on the right, we have this nice smooth motion. Additionally, when we tune the interpolation, we can specify the number of interpolation steps. The number of interpolation steps basically tells you how long do I want to make that interpolation. If you make that interpolation very short, your robot's going to have to jump from one position to the next very quickly, and that causes this kind of big discontinuity in the trajectory. Whereas if you make it too long, then it's basically going to be trying to move a very small amount of distance in a large number of time steps, and that's going to cause laggy behavior. And so this interpolation is something that you need to tune for your specific task. If your task is very quick and has a short number of time steps, maybe you don't need a big interpolation number. If it's very slow, then maybe you'll want a larger number. Lastly, we described this a little bit, which is action noise. Action noise is something that we include as part of Groot Mimic, and this is something that is usually will lower the success rate of your data generation, but has the benefit of training more robust policies. So it's always recommended that when you use Groot Mimic, you add a certain level of action noise so that your policy can be more robust to small deviations. So
it makes the demonstrations look terrible.
Yeah, it makes the demonstrations look bad. The trained policy looks better. So it's kind of this inverse thing.
Yeah. Yeah, interesting.
And then there are some other parameters here that you can also tune. We have more information about this in the documentation. These parameters are kind of less critical to tune. They're related to some small nuances in how trajectories start and end, how we select the human source demonstration. These can have basically some smaller impacts on how your data set looks and how the data generation success rate, how if it can be a little bit higher, a little bit lower. But for the most part, the remaining parameters are less critical to the data generation process. So the main takeaway here is that when you try to do data generation with Groot Mimic, these parameters shouldn't be just viewed as completely independent knobs. They kind of need to be tuned holistically and somewhat tailored for different environments. We provide a heuristic here, which is the recommended ordering, which is to start with subtasks. Your subtasks are kind of fundamental to the entire data generation pipeline, so you want to get those determined first. After that, you can determine, you want to kind of set the level of action noise you want. So if you have a lot of action noise, get that kind of determined in there early on. After that, you can then go into some of the other parameters, and you can tune the number of interpolation steps and the remaining parameters to try and get the data set to A, be able to generate at the success rate that you want, and B, to look a particular way. And more information on these configuration parameters are available in the Isaac Lab documentation, you can see there sort of examples in the source code where all of these things are defined and how you can change them.
Amazing.
Yeah. So that was the main kind of tips and tricks I wanted to give for Groot Mimic. Before I move on to the next section, which will kind of talk a little bit about Groot Gen, is there any questions or
there are a bunch of questions, but I'm going to suggest actually because I think the information you're presenting is so valuable. I feel like we should continue with your presentation, and then time permitting, circle back at the end. Or if we do run out of time, we'll put a link to the Discord Isaac Lab channel and ask people to go there to post questions, and then all us as a group can go hit Discord, later today and start answering some of those questions. If that sounds good to everybody here.
Yeah, sounds good to me.
Okay.
Yeah.
I also invited a very special guest. We'll see if he pops in a second. Someone from the community who's actually in the chat. I thought it'd be cool to have him come up on the panel and give his feedback. So we'll see if he pops in a second. But go ahead, continue.
So then, I guess this will be the last section of this presentation. So we talked all about Groot Mimic, and Groot Mimic was all about motion trajectory, and that already allows you to expand your data set dramatically. If you have different motions, you're teaching your robot to do things in different ways and allow it to learn how to complete the task in a variety of ways. But we didn't touch about any of the visuals. So if you have a robot running around in the world or in simulation, and you're putting it in a different scene that looks different, then how do you generate data for that? And that's where Groot Gen and Cosmos comes in. So when we take Groot Mimic and connect it to Cosmos, we're able to take this kind of diverse set of motion trajectories and then add additional diversity on top of that in terms of visual diversity. So far, all of our trajectories have had the same visual setup. They all look the same. They're just different motions. But now with Cosmos, we're able to augment each trajectory and turn it into tens or hundreds of different visual environments. So we have workflows for this coming in the future. So here I'll kind of just give a teaser and an example of how this would look and how Mimic trajectories fit into Groot Gen and Cosmos. When we generate with Mimic here in Isaac Lab, we have the ability to generate RGB as well as segmentation output. And so on the left hand here, you see a Mimic generated trajectory with these two, RGB image and segmentation. And then with this output, we're able to feed this into Cosmos to basically add in a ton of visual augmentation. So with the relatively flat and low resolution image on the left, we're able to basically change, in this case on the right, the texture of the table, the texture of the robot, the background, the lighting, so on and so forth.
That's amazing.
That's amazing.
That's amazing. And I think for people, I don't know if you didn't explicitly say this, but we talked earlier about how you can train one of these models off of state or off of vision. And if you're going to train a model off of vision, you need a huge variety of just visual differences to get that to transfer to the real world, and which in the past was, I mean, just undoable, right? It was just you should really couldn't get enough.
It's a perfect
variety.
opportunity actually to bring in Kamate, who's here. Let me bring him. Let's say hello
yeah.
to our very special guest in the community who I just met at GTC. I saw him active in the chat. Kamate, how you doing?
I'm doing great, and I really enjoy Peter, your presentation. This is excellent.
So this was not planned. I saw him in the chat, and I'm like, hey, why don't you just come in? Because he had a great bunch of questions and comments. So Kamate, feel free to jump in at any point with any kind of comment or question. You represent the community right now, so welcome. And but very, very fascinating stuff. Kamate, do you want to briefly kind of introduce yourself a little bit so people know about your background?
Absolutely. My name is Kamate Richards. I work for Amazon AWS Robotics. I'm currently our robotics community leader, and we're actually kind of realigning under a new title for called Physical AI. So an excellent. I've been part of this community for years in the background. Really enjoy meeting Edmar in person. And I think I met a few of you in person as well. So, next week I'll be at Humanoid Summit in London. If any of you will be there, I know we had Jim Fan at our last summit. So hopefully to see some NVIDIA team members there would be great.
That's awesome. Jim Fan, he's like first of all, thank you for coming, those kind words, and for being such a good member of the community. You should follow Kamate too. He's got great posts on LinkedIn. But yeah, Jim Fan, he's a rock star now. He's a legend. You should also follow him on LinkedIn. Really insightful posts regularly. But okay, thanks for introducing yourself. Peter, feel free to continue on, and then we'll jump in and tackle some of the questions as we progress.
Yeah, definitely. I think this is getting to the end. I know we're a little bit over time, but this is just I just wanted to, with this slide, kind of show the capabilities of Cosmos and what you can do when you connect this to Mimic. So you can see on the bottom here we have that same scene just randomized visually in all kinds of different ways, changing lighting, changing texture, different type of object. Object textures, object kind of shading, and so on. So when you combine Cosmos with Mimic, you're basically instead of having to do all these randomizations in simulation, where you would have to have 3D artists generating new assets, you'd have to rerun rendering on every single scene, and which all adds to even more compute resources required for data generation. You're now able to do this with a in post after you've generated trajectories. And let's say you create one and you don't like it, you're able to very easily go back and change something completely. Instead of having to recreate a bunch of assets, you can change a prompt and that will change the texture of the table or the scene in the background. So this is something that we're very excited about, and we'll be bringing workflows for this soon in the near future. For now, we've released a kind of teaser of this as a blueprint, part of the synthetic manipulation motion generation blueprint. So you can go on and try yourself generating this a couple of Mimic trajectories and then running it through Cosmos. But we'll have more full workflow of this in the future. So then to kind of just wrap up, the main things that we covered today, and the main things that wanted to drive home with Groot Mimic, is that this is an automatic motion data set generation tool for manipulators and humanoids. Mimic is meant to generate a vast amount of motion trajectory data from a very small number of human demonstrations. And this is ultimately done to minimize the manual human effort required for data collection. The generated data in our tests have been on par with human demonstrations, and we're able to train successful policies with high success rates using this synthetic data. And ultimately, as we're training more and more complex robots and want robust robotic policies, Groot Mimic is a very powerful and economic tool for scaling up robot learning and scaling up that that data pipeline to give you the data that you need to train robust policies. And with that, I'll leave a slide here, which is on additional resources. So all this work is available in Isaac Lab. So you can download Isaac Lab now, install it, and be able to run for yourself Groot Mimic. In there, we call it Isaac Lab Mimic, and there's a separate tutorial for that. I also linked here the SMMG blueprint, which connects Mimic with Cosmos, and you can try that out for yourself. And lastly, for anyone who's interested in some of the more theoretical aspects, there's a number of papers that describe how this Mimic process works and how basically all this work was based on the theory from those papers.
Absolutely amazing. Thank you so much, Peter. It's fantastic. And I have to give also a very special thanks. Let me bring her up here. She's been amazing in the chat, helping people with all these answers. Shinshu, how are you doing?
Hey, thanks for having me here. It's really good pleasure to see everyone posting a lot of questions in the chat. Just one note here, if you have any more questions, please come back to us. We would love you to try our Mimic workflows, and just stay tuned for the upcoming release, as we're also releasing the end-to-end workflow of using Mimic to fine-tune the VLA policies, for example, Groot.
Amazing.
So the official channel for Groot Mimic support, is that the Isaac Lab GitHub repository? Is that where they should ask questions?
Yes, if you have any questions on Groot Mimic, feel free to add that on Isaac Lab GitHub, and we will see them and respond from there.
Thank you for mentioning that, Eric. Yes, support is a little different for some of these different things, right? Some of them go to the support forum, some of them go to the GitHub. So this is use GitHub for that.
Yeah, Edmund, so I think it's a good point for me to also say that this workflow, definitely, I'm so excited seeing a lot of questions about Groot N1 model and all of those things. And shows that there's a lot of interest in the community about that. And we have a announcement tech blog that just went out about the new releases that are coming up. So we're going to be looking at how to merge Groot Mimic data set, convert it to layer robot data format, and then use that to actually fine-tune Groot N1. And I'm sure that's going to be a lot of that's going to be exciting to the community. I want to see, how do you want to use Groot Mimic? How do you want to use Groot Mimic plus N1? How do you want to use Groot Mimic plus Cosmos? And please do let us know what exciting project you would like to work on, and we'll definitely supply you with all the resources. Thank you.
That's fantastic. Thank you so much for calling it out. Big thank you also to Amelia, who's working like a champ in the chat as well. Okay, so first, I would love to get your feedback on this, Kamate, because you're an expert in this area. You've been very educational in your posts on LinkedIn, your videos. You have a fan earlier I just saw. Let me see, where is it? If I can bring it up really quick. There it is, from Lychee AI himself. Big fan. So, what's your take on this?
This is excellent. I am also pretty involved with the Lay Robot team and Remy over in Hugging Face, and we would love to integrate this into a lot of the work that we're doing on a continuous basis. So certainly that would be one of the first things. And I'm actually staring at a bunch of SO 100 arms and 101 arms. If you're interested in how those work, I have some sitting right next to me.
That's great.
And then the other thing is the full pipeline. We're really interested in the Apple Vision Pro that you showed earlier. Is that full pipeline available today for us to start looking at? And is that there's announcements every week, so I can't even keep up with the some of the announcements that have come out. So if that pipeline's available, if you can point us toward those resources, I'd love to check them out.
I have a hard time keeping up, and I work here.
Yeah. So yes, the pipeline is definitely available right now for use. So you can connect your AVP with your manipulator. So we have the example for the Franca arm, and also you can connect it with the humanoid. We have the example for the GR1. So all of that is in the same documentation in Isaac Lab, the teleoperation and imitation learning documentation.
Okay, I'll be going through that today because I'd love to show that at the Humanoid Summit coming up next week.
That's awesome. That's exciting. Okay. Now, Shinshu, I know you've been answering a lot of the questions. Is there anything that you didn't get to answer in the chat or that we didn't get to post, but you want to address right now on voice?
I think I'm good. I should cover most of them.
Okay. All right, cool. All right. So we have we have his note from Lychee. I'll put it on the screen here, but he's sharing with, and I highly recommend that you follow his channel. He's also got a Lychee AI Hub, which is a website that consolidates a lot of resources, not only from himself, but from other community members. But he's got tutorials planned on the robots, SOARM, Groot N1, and Cosmos. So, so thanks for those great words in the live stream. But really, really awesome to have this panel here. We have a record number of viewers, I think, watching in office hours. So that just really speaks volumes about the level of interest in the community on this topic, but also just about the information that's available now is making this so much more accessible to developers than ever before, which is just fantastic. So thank you all for preparing and coming on and talking about this. Is there any kind of, I know we're a little over, obviously, any kind of other points you guys want to make, or do you want to go through a couple quick questions, or do you want to kind of just wrap it up and we'll invite people over to the Discord?
Well, I'll be over in Discord in 15 minutes. And
that's right. So there's an Isaac Sim and Isaac Lab study group, which takes place every week at 12:30 p.m. Pacific on Wednesday. So that's happening in about 13 minutes from now if you're watching this live. So we invite you to come over on the Discord server. Very easy to get to. I'm going to offend a marketing team again. I would like you to look away. There's our Discord server address. So anyone who wants to come to Discord, there it is. Just NVIDIA Omniverse. And then the marketing team, you can look at the screen again. So that takes place every Wednesday. There's basically a channel on our Discord server or category that says study groups. If you go to that category, you'll see right under there's one called Isaac Sim and Isaac Lab. We have another one for OpenUSD, but you're welcome. You can come. It's just like this. You can turn your webcam, turn your mic on, and ask away. It's a great place to discuss. So that takes place in a little over 10 minutes from now. Okay, so any other areas though that you guys wanted to cover before we bid adieu?
Yeah, I think one last question I might want to see is the question of how well Mimic is able to randomize contact-rich tasks. So the two papers that Peter shared, there's one of the tasks there that is for contact-rich manipulation, which is for J assembly. So I think that is something that you can look at to see how to generalize that to your own specific application.
Okay, cool. I'm going to throw this in there. This is a last minute kind of question here. Quick question from Snappy Guy. I don't really leave Snappy Guy hanging. Is there any way to run pre-trained models on either native GR1 or other humanoid in Isaac Sim?
Yeah, so I'd say maybe the easiest way to do that would be through Isaac Lab and creating an environment. So in Isaac Lab, if you create that environment, and then that environment acts as kind of the bridge between your pre-trained model and Isaac Sim there. So then you'll be able to basically run inference of your model in any format that you want, and then the output of that model will be pumped in through actions to then control the robot in Isaac Sim. We do have some reference examples of this coming up soon. So kind of stay tuned for that, but it will be, again, built off of this Isaac Lab platform.
Amazing. And a wonderful comment from Julius Caesar himself. NVIDIA has done a great service to humanity, opening this to the public. Well, I have to say, NVIDIA is nothing without the developers out there. All the developers out there and doing their life's work, using these technologies. It's your work that actually makes this all worthwhile, and it's very inspiring and motivating to us at NVIDIA. So again, for us, making this as accessible as possible is so critical because of everyone out there working on this stuff. So thank you. Okay. I have one more question. I'm sorry, I lied. One more, last one. Can we integrate Yaskawa manipulators with Isaac Sim? This is we're talking about Isaac Lab more now, but is anyone familiar with this one?
Yeah, so I'm not too familiar with that. However, I think Isaac Sim and Lab should be very flexible to integration of basically any robot platform. So as long as you have the robot models, USDs, all the correct definitions there, it should be possible.
Great.
And also just want to do a follow-up with Snappy Guy's questions. So for your ask, you can also try with the ROS bridge in SSIM, so they can also directly run the closed loop script in SSIM. And for the official support of Groot in Lab is coming soon.
Fantastic. Okay, just some great comments flowing in. I'm just putting them on the screen here.
I just did a quick Google search, and yet there is you can use Yaskawa manipulators with ROS2. And so if you can connect it to ROS2, you can do about whatever you want.
Great. Fantastic. All right. So now we leave on a very high note. Thank you, everybody participating in this panel. Thank you, Kamati, for coming in the last second. Really great to see you. Shinshu, thank you so much for all your help in the chat. Amelia, amazing producer, has been helping also in the chat. Thank you very much. Especially Eric, Peter, Oyinda, thank you so much for your expert guidance here, showing the world what's possible and giving them the resources. If there's any resources, links you missed, just come over to the Discord server into the Isaac Lab channel, and we will be sure to provide there. Peter, is it possible? Is your deck available? Can we post that in the Discord maybe?
Yeah, definitely. I'll share the deck with you, and then we can get that posted.
Awesome. So there's a reason to come on the Discord. I'll share that on the Discord server on the Isaac Lab channel as soon as I get it from Peter, and then you'll have the active links in there to use. Thank you so much out there, everybody, for watching. It's been an absolute pleasure. Some of you will be in the study group in a few minutes on Discord. For everyone else, we'll see you on GitHub. We'll see you on the forums. We'll see you next week on the live stream. Don't forget to like and subscribe. Very important, so we know what content is important to you, and we'll keep doing it. It really helps us. So go ahead and do that right now when you have a second on this closing screen. And again, thank you, everybody, for joining us today. Really fantastic session.